and I'm going to start recording for the record, which is now recorded, can have some weird connotations. So if you referenced someone's size, what are you talking about?
Weight.
Weight, okay? But a really tall person you wouldn't say is big. So there's mass, and there's also volume, there's height. So when we say big, that language is weird. If we say size, that language is weird. Does that mean they weigh a lot? Does that mean they're really tall? Does that mean they're really strong? Does that mean they're weak? There's so many different ways you can describe size. So when we talk about organic chemistry and we're talking about size, is referring very specifically to the volume of that atom. It has nothing to do with mass. It is volume. Okay? So what dictates the volume of our atom? The electrons. So when we're talking about size, we're talking about our volume and ultimately our electrons and where the electrons are located. Well, how do we know where the electrons are located? That's all that atomic theory stuff that we're trying to remember. Okay? And this is where size becomes an interesting challenge on our periodic table. Okay? If you add more electrons, what would you expect to happen to the size?
Increases.
It increases. And it turns out that if we look at hydrogen with how many electrons? Yes. 1, you were right. 1 electron for neutral hydrogen. And we look at lithium with 3 electrons for neutral lithium, more electrons, it gets bigger. That makes sense. Okay? And we could even throw in sodium, I don't have that one memorized, sodium with 11 electrons, bigger. So it's getting bigger and bigger and bigger and bigger. Okay? That one's okay. The real challenge is when we move left to right. When we look at lithium, lithium has 3 electrons. We jump to boron, it has 5 electrons. Since it has more electrons, what would we expect to happen to its size?
Increases.
It should increase. Instead, what happens?
Stays the same.
Okay. And this is where we run into some gray area, and I love the stay the same answer for the record, because that's what the video said. Remember that it stays the same. Officially, what does it actually do?
Decreases?
It gets smaller. Okay? And there's some competing things that help to explain why it gets smaller. Ultimately, that size difference, left to right, within a row, is such a negligible effect, such a small effect, that we don't care in organic chemistry. Okay? Which is why in the video I say, it doesn't change. Okay? It's a negligible effect. And I've had several people yell at me for saying it doesn't change. Okay? Which is why I have to hem and haw a little bit. Okay? But it's such a small effect that when we look at atoms across a row, we would say their size stays consistent. Okay? Why does that become important? Well, when we're talking about organic chemistry, we're talking about how things interact with each other. Okay? So let's say you want to interact with the pencil. What are you going to try and do? You're going to grab the pencil. That's pretty straightforward and easy. But you can only grab the pencil by making it through my hand. Okay, that becomes significantly harder. So you might need a pair of tweezers to reach through the hole to grab the pencil and pull it through. That's going to change how you interact with just that macro scale thing. The exact same thing happens on the chemical level. Okay? So the size of our individual atoms and where they are located relative to each other can affect how reactions happen or don't happen. So we need to have a passing understanding of size of our atoms so that we can come up with those predictions. And when does that size difference matter or not? Okay? When we're moving down the column, the size will matter a lot. Left to right, the size has a negligible effect, so we would ignore it. Kind of make sense? Okay. And that, it's a tricky one, which is why there were probably pseudo-tricky questions within that. Okay? Or I'm calling pseudo, you can call full tricky, that's okay. Make sense? Yep. Okay. We also have to be aware of orbitals and electronegativity. We okay with those? Is that a question? Yes, maybe?
Is the SPP and all That's the only.
Yes. So our orbitals is what orbitals are our electrons located in. And because we're looking at a simplified table, those first two columns would be our S. Our outermost electrons are in the S. And then for this side, we're looking at our outermost electrons being in the P. Okay? And that's really all you need to get out of those orbitals, because what we end up doing is tweaking our understanding. That only works for atoms. Almost everything we do is we bring multiple atoms together to make compounds. I can't use the same theory, it turns out, because those are atomic theory versus molecular theory, and so that changes our interpretations of how we look at things. Okay. The other big one, just because, electronegativity. Everybody okay with electronegativity? Pop quiz. Which one's the most electronegative? Fluorine. Okay. Least electronegative? And if you say francium, I'm going to say no, because what you're looking at is a real periodic table, and we're organic chemists. We don't look at real periodic tables. We look at a bullcrap hand-wavy one that's on the screen.
Is it cesium?
It's potassium. I don't see CS on our periodic table. But people are like, oh, it's cesium. Yeah, it's there. Remember, organic chemistry, simplify the periodic table. Okay, we can pretty much ignore cesium and francium and rubidium. Okay, because we just won't work with them, so we don't have to stress about them. Okay, I don't expect you to have this table memorized. I just want you to be kind of aware of those shifts. Atoms to compounds, interactions. We all good? The shaken or stirred analogy made a whole lot more sense in my head, and then I watched the video over a couple times, and then it made no sense. And I don't. Okay. This is something that's going to keep coming back and kind of haunting us, that I'll complain about, bonds versus forces. We need to be very careful about this. When we talk about OChem, we will look at bonds breaking and making. We will also talk about forces making and breaking. They mean very different things. Okay? The analogy that we could potentially use, just because you're in the front row right here, closest to me, there is a force that connects us. That force can be relatively easy to break and form. Okay? There's also a force, an attraction, between my hand and my body. If I break that, that's a pretty serious thing. Okay? That requires lots of energy. The interaction to break the connection between individuals, much easier to do. That's looking at forces. The interaction to break something that holds its identity, that's now looking at a bond. That's significantly harder, and that's a whole different focus. Make sense? I'm really irritated this isn't letting me advance slides. Okay. Which would get us into kind of our starting point. When we're looking at organic chemistry, okay, we need to know what it's about. Okay, well, organic chemistry, for the most part, is the study of carbon. Okay, how carbon interacts and forms compounds. Turns out it's a little bit narrower than that. We almost always reference it as carbon and hydrogen. Even then, that's a gray area. Okay, so for instance, carbon dioxide, that has carbon in it, doesn't have hydrogen. Is carbon dioxide an organic material? Okay. It's kind of a strange question, and depending on who you ask and what they've been studying, they'll phrase the answer differently. Right? So there isn't a necessarily clear-cut definition behind it, but for the most part, what we're looking at is, could an organic material or a living thing process that carbon structure? Okay, for the most part. Okay, so carbon dioxide is processed biologically, okay, as a byproduct, so we might reference that as an organic molecule. Okay, so if we're looking at this carbon compounds, we need to know what carbon is, and we need to know what compounds are. So what makes carbon?
Protons, neutrons, electrons.
Okay, so things that have protons, neutrons, and electrons are carbon. So we got to refine that definition a little bit further. So when we're talking about carbon, we're referring very specifically how many protons it has, how many electrons it has, and how many neutrons. This is why we have to have an understanding of atomic theory, because that's what creates the identity of what makes it carbon. Okay? Of that, do we need to know all of it? Do we need to know how many neutrons? No. Do we need to know how many protons? Not really. Our primary focus sits in on the amount of electrons and, kind of more importantly, very specifically, which electrons. Okay? What we're looking at is effectively two carbon atoms and how they interact with each other. What's the thing that interacts between them? If we were to reference this as an atom, we might go through and say we have our protons and neutrons in here and we have our electrons out here. What's the thing that interacts when I bring those two smiley faces near each other? The outermost thing, which is our electrons. So even though carbon has 6 electrons, I don't care about all 6. I only care about the outermost. Well, what is outermost?
Valence electrons.
Valence electrons, which isn't technically the outermost, it's the outermost energy level, the second energy level. And in that energy level, we have 4 electrons. We have 2 s electrons and we have 2 p electrons. Okay, we have 2 electrons in the 2s and we have 2 electrons in our 2p, which gets us 4 valence electrons. Their locations in those s and p orbitals becomes important because those electrons can now share with something else. So I need to understand something about that atomic structure that allows me to build it outwards. Kind of, sorta? Yeah, having to go back and forth. I'm really going to have to fix that. Okay? And then what makes it as a compound? Okay? If we're looking at these happy, smiley things as people, when is that person a couple? When do I have a pairing of people?
When they bonded,
How do I know they've bonded?
when they share electrons.
How do I know people have bonded?
Oh.
They're together. So if I stand next to you, we're a couple? You're like, I hope not. Okay? So there's something deeper that happens out there that becomes a little bit more challenging to tangibly relate with people. You might do it with, well, wedding rings. Yes. Okay? There's a symbol that would allow us to do that. When we move to atoms, okay, it does have to do with the proximity. Okay? Again, we wouldn't say these 2 top circles are bonded. We probably wouldn't say the middle 2. Why are the bottom ones now considered bonded? They've somehow been satisfied. How do we see that? They look happy we changed the pictures. Okay? How do we do that with atoms? If I want to bond carbon with carbon, how do I know those 2 C's are bonded? This is coming up with a special notation showing the line. If we were going to say they were bonded here, you'd probably be like, I don't think I would ever draw that. Well, why not? It's pretty simple. The carbon with the line to the other carbon. Why do you think you would never show that as a bond? I mean, it is a bond. It's showing the dash between it. Why is that not a particularly useful one? The size of the distance between them. So what we try to do is draw them as a notation closer to each other so that we can represent that bond relatively quickly and efficiently. That allows us to better see that. We're still taking advantage of that distance, bringing them closer to each other, but they have not officially formed a bond until we see that line. If I erase that line in between, these are now independent atoms and I have not shown a clear connection to them. Are there exceptions? Absolutely. We'll deal with that in a little bit. Okay? But what we want to make sure we see is those lines that define that bond, because that helps us. Okay, well, how do we define that bond, which is what I believe okay, there's our atomic theory, we're reviewing all that, we're good with that, where our electrons exist, our outermost, okay, our S's and our P's. For our carbon in particular, okay, we said 2s and 2p2. Okay? That was a bit kind of reductive. When we look at the S, 2S, there it is. That's what it looks like. What does the P look like?
The dumbbell.
The S was one circle. What does the P look like?
Hourglass.
I accept dumbbell as a shape. We'll try it again. The S is one circle. What is the P?
2 circles.
3 dumbbells. Why is that important? When I go through and look at the atomic configuration for carbon, we would have our 2s orbital. We could say it's a line representing the orbital, and it has the 2 electrons in it. We could show the 2 electrons. When we draw out the P, we would draw 3 2p orbitals. Okay? And there's 2 electrons in them. 1, 2. I guess officially we would draw it paired. Why did I not draw them next to each other?
Because you have to fill that third one before you can.
I fill the lowest energy first. Okay? As soon as I put an electron in it, there's another lower energy state, so I'm going to fill that one before I pair. Why did I pair the 2s?
Because there's only one.
There was only one at that energy level. So this diagram immediately implies an increasing energy associated with it. Kind of, sort of? It should be all the way back at the beginning of Chem 130. Okay? That's now our fundamental structure for our carbon. There are some things that we could do within this. When we think about our atomic configurations, okay, we could look at our noble gases. And in the noble gases, when we go through, particularly for the noble gas next to carbon, we're looking at neon, and we fill out neon's electron configuration. What do we know? Well, the difference between carbon and neon is what? C versus Ne, yes. What other difference? Number of protons. Phenomenal answer. What do we say how important protons were? They weren't. So great, that is a difference, not useful. Try again. What did we say was the most important thing for us?
Electronegativity. Did you ever say that?
Electronegativity is important,
Electrons?
but electrons. It's just the electrons are important to us. Electronegativity is the property of how we hold those electrons, which is important. So what is the electron difference between carbon and neon?
Is it 4?
It is 4. Carbon, neutral carbon, has 6 protons and 6 electrons. Neutral neon has 10 protons, 10 electrons. So the proton count is different. We see that immediately because the symbols change, because protons define the element. Okay? We would also see it immediately because the number in the upper right-hand corner tells us that information, the number of protons. Okay? We know it has 6 electrons and 10 electrons because we're saying a neutral, which means the charge is balanced. If carbon had 6 protons, what would its charge be? Just a carbon atom with 6 protons.
And no electrons?
No electrons.
Oh, then +6.
Positive 6. That's not neutral, it's positive. Okay? We need to crush all optimism, so what do we got to do? Add electrons. Add a negative thing to it until it is perfectly balanced. So how many electrons would I have to add to neutralize 6 positives?
6 electrons.
6 electrons, because each electron is negatively charged. Yeah? Okay. We do the same thing with our neon. We could now look at the difference between them as far as our electrons go, because electrons were the most important. We're talking about 4 electron difference. So if I'm looking at my electron configuration for neon, I would need to add 4 more electrons into my picture. 1, 2, 3, 4. Neon as a noble gas. What can you tell me about the noble gases? Does that mean nothing? What can you tell me about the noble gases?
They're stable?
They're stable. Awesome. They don't react. Okay? And if we think back to fundamental, we had ionic charges that we were supposed to memorize. Does that ring any bells? Calcium has what charge? Sodium has what charge?
Plus one? Is it plus one?
Plus one. So you shook your head. That's why I'm checking. So plus one. Now the fun one. Why is it plus one? See, this is one of the... 130 should have told you why it was a plus one.
It likes to lose an electron in order to satisfy an
It's valence shell.
Yeah. It just likes to lose an electron because it's the easiest.
So that it can become more stable.
Yeah.
Why is it more stable? What does it start to look like?
A noble gas.
A noble gas. And our noble gases were stable. So why does sodium become a plus one? If I get rid of one of those electrons, what happens?
It wants to be like neon.
It looks like neon. Could it look like helium? Yes. What does sodium have to do to look like helium? What's that? More, that's good enough of an answer. It has to do more work. It has to lose 9 electrons. That's a whole lot more work. It doesn't want to do that easily. So what it does is it loses 1, which means sodium carries a plus 1 charge when it becomes charged. Well, so does that mean they always lose electrons? Well, fluorine.
Negative one.
Why did it become negative?
Because it wants to gain an electron to be like the next double
The
gas.
easiest thing for it to do to look like a noble gas is to gain 1 as opposed to lose 7. That gaining of 1, it's gaining an electron. What charge is an electron?
Negative.
Negative. If I add more negative to it and 1 negative, it becomes negative 1. What happens to oxygen?
Negative two.
Negative 2. So that pattern for our ionic charges also manifests with our compounds. When I look at how carbon bonds, it's bonding to look like a noble gas. Okay? So what it could do would be interact with another atom that supplies 1, 2, 3, 4 electrons. Okay? So how many times do we think carbon could bond?
Four times.
4 times. Why?
Because, you know.
I don't accept that.
There's only room for 4 electrons.
So we wouldn't expect 5 because there's not another space to put the 5th, but why 4 and not 3?
So that it can complete its shell.
So that it can satisfy all of those holes. So we can see those holes in it. Okay? If we scaled this out to oxygen, what would oxygen's outermost shell look like? Well, we go to neutral oxygen, it has how many electrons?
8.
8. Okay? We've got the 1s, so we ignore. Okay? And we've got the 2s and the 2p. It's in the 4th column of the p block, which means it's 2p4. I only have 2 electrons in here, so what do? For oxygen, it now has 3. It now has 4. How many bonds would I expect out of oxygen? 2, because there's 2 places that electrons can be deposited. Okay? So knowing something about our electron configurations can help us predict possible bonding patterns. We have to be careful. It's possible bonding patterns. Kinda, sorta? Okay. So that's where our electrons are. The next part is where they exist, which is going to become important. The S is a sphere around the nucleus. The nucleus is sitting right in the middle. Where's the nucleus in a p orbital?
Where the axis is crossed.
Yeah, right in the middle. Right? So our electrons are kind of dispersing into these strange shapes. They're probabilities. Okay? So if somebody came into this classroom, they could describe the probability of where they would expect to find students. Right? So if I asked you to predict what that would look like, where would you most likely find students?
The back 2 rows.
The back 2 rows. Why? because the instructors are scary, jerk, and no one ever wants to talk to the instructors. So we sit at the back and we avoid them as much as possible, and then it slowly fills forward. It's because he spits. That's what it is. You need splash guards for the front row. It's just like a camel. Sorry, the analogy is just going further down long directions. Okay? So you could draw kind of shapes and say, well, more than likely for our class, we would expect the electrons, our students, to be back here. They might be filling it in here. There's a very low probability here, and there's not so much in here. How do we see that in our diagram? How do we know it's a higher probability at the back? What does this diagram show us? Why is it a low probability at the very front, high probability at the back? It's big. It's a big circle. That's literally it. Okay? How come there wasn't any shapes in here? Why did we not show this, say in blue, something like this, as the pizza shape?
Because then it would just be one shape and it wouldn't show the different probabilities.
Nope. What is in that space? This room. Remember this room. No students can be in that space. Really? You're saying when you're in here, there's a space that you won't sit. Where is that? You can do a little bit better than that. Closer to home. Closer to where you are. Where's no one sitting? On the table. That's the table in between. Electrons can't exist there. Okay? The floor's you're right, the floor covers some of that, but the chair scoots back and fills some of that space a little bit. So I would argue less that. But for sure, no one's sitting on the table. Okay? So there's a 0 probability of finding someone sitting on the table. Okay? So our shapes and the lack of space tell us something about where people are likely to sit. The same thing is happening with electrons. When we look at this sphere for our S, what are we saying? The electron is equally likely to be found anywhere around the nucleus in that entire space. When I show this dumbbell, what does that mean? That means the electron is allowed to be found above the nucleus and below the nucleus, but it will never be found at the sides for this shape. For the next shape, it now is found at the sides, but not above or below. The next shape, do what? How do you, 3 dimensions. Okay, in front and back. Okay, that's what we're trying to predict and kind of approximate with those, is where our electron is allowed to be. Why does that become important? What makes a bond? Electrons. Okay? And in particular, it's the sharing of those electrons. The only way we share is when they're occupying roughly the same space. So we have to know where our electrons are to describe how they're forming that bond. Apparently I just decided to take a picture. That was fun. Okay. So we've got our periodic table. We could look at electron configurations. We just kind of touched on electron configurations. Okay? Getting us some basic kind of bonding patterns behind it. I would argue you should go home and you should do that for some elements. Should you be doing it for all of the elements? No, why not? We don't use them all. You mean we watched a video that said, among other things that were frustrating, that we don't use all the elements and we should only focus on like 10? Yes. So draw your electron configurations for those 10 and predict what you might expect their bonding patterns to be. Okay? Based on just filling out those electron configurations. Does that make sense? That sets you up with kind of a decent baseline that would allow us to kind of push further. Okay? And what are we going to push further into? That's now moving into our compounds and how we define our compounds. Okay? So we're going to bring atoms near each other so that they can share electrons. They can put those electrons into a bond, which is going to get us really close to Lewis theory. Okay? before we push fully into that, we need to make sure that this concept of electronegativity exists and we know what it means. So, we said we were all good with it in our quick review, right? What is electronegativity?
The ability of an atom to bond with the electrons of another atom.
How likely it will lose or gain electrons?
How likely it will lose or gain electrons? No. Combining both of your explanations gets pretty close. Okay? Electronegativity is always about the ability to steal electrons. So it's not gain or lose, it's always stealing electrons. But it's not stealing just any electron. Stealing an electron from nothing, like there's just electrons in its space and I grab it and I own it, that's not electronegativity. Electronegativity only is presented and discussed when I now look at a bond. When I look at the ability for blood, as electrons in this analogy, to be shared between my chest and my arm. That's an electronegativity. Okay? And we could actually push that analogy. Where is the most electronegative part of my body if blood is electrons?
The heart. Is the most one?
I don't know enough about biology. I wasn't going to say the heart. The heart's pretty good.
You say muscles?
I don't know. You guys know biology. You're all supposed to be like nurses and stuff, right? Not me.
I don't understand the analogy. Is it the brain?
Why the brain? That's what I would have said.
Because it's like where everything happens basically.
It's where our existence ultimately is. You chop off the arm, okay, you still live. You chop off your leg, you can still live, right? You chop off the heart, and I mean, you start butchering the body enough, like you don't still live, but roughly with those analogies, okay? You can lose a heart and still live, right? Like, no, you can't. I can put in a fake heart, I can put in a pig heart, and you still live. I remove your brain, are you still the person you are? So I would argue that your brain is the most electronegative thing. Put your body under stress, where does your body push blood? To your brain. This is why when you get frostbite, what do you lose? Fingers and toes. You even lose your nose, okay? Because the blood is focused in your core in trying to maintain those functions to keep the brain alive. Isn't it? Again, you're the biologist people that know this stuff, not me. I'm just making stuff up. You shaking your head saying no, I'm not right?
No, you are.
Oh, okay, good. I'm not always right. Does that kind of make sense?
Yeah.
So when we're looking at electronegativity, it's how things share within a bond. So what we would do is bring two atoms together next to each other, and they bond. How do the electrons share back and forth? Okay? Depending on how they share is going to classify and define that type of bond. And that's where we get the bonding patterns. Whoops. Are ionic. Come on. Are ionic, polar covalent, and covalent. Those categories become important for us so that when we look at a structure, we can identify those bonds and we now know something about their properties. When I look at an ionic bond, okay, that's a bond between a metal and a nonmetal. The difference in electronegativity there is massive. So massive that what do I end up seeing? I end up seeing something along these lines. Sodium and oxygen. Sodium is a metal, oxygen is a nonmetal. I put them near each other. The connection between them is technically an ionic bond. As an ionic bond, what happens? The oxygen rips the electrons away from the sodium, and I form an ion. The sodium, who just lost electrons because its electronegativity is so much lower, forms a cation. We're forming ionic systems. That's where our name ionic bonds are coming from. Okay? Typically, how we would represent it is without the line, and we would show the charges. Because it's not really a bond, depending on the scenario we're looking at. And most times we're looking at it in solution, and the ionic bond breaks. Okay? The rest of our structure is now looking at, or the other scenarios, if we don't bring in metals, is we're now looking at polar covalent and covalent bonds. The properties of those are dictated again based off their electronegativities. Covalent bonds are going to be defined by equal sharing of electrons, perfectly equal. Okay? So that's the exact same element bonded to the exact same element, carbon and carbon. Okay? Equal sharing of electrons, we now have a relatively strong bond. Those electrons aren't moving one way or another, which means no charges, which means there's nothing to stabilize. Okay? Same thing's going to happen, ballpark, with carbon to hydrogen. The difference in electronegativity there is so small that we can just call that neutral, and now again, a relatively strong bond. The polar covalent bonds will be anything and everything else. Okay? Why did I pick this molecule for this particular slide? Phenomenal answer. It's because all of those bonds are shown in that molecule. We just addressed the ionic bond. Where's a covalent bond?
Is that shape carbon?
Here's where we encounter a problem. Okay? When we move to organic chemistry, our structures get vastly more complicated. Because they get more complicated, we start to make abbreviations. Those abbreviations remove information that you might have had in chem230. You no longer have access to in OChem, or you will very quickly lose access to, arguably at the end of this week. Okay? Here I'm being a bit preemptive and removing it all. Okay? We need to fall back on the things that we do know. The line represented a bond, which means all of the lines I see within there are bonds. Okay? What are the things connecting the atoms in that bond? Okay? So I've got an oxygen clearly there. What is that oxygen connected to? Is it connected to another oxygen? No, why not? Because there's another line up there. So that negative oxygen is connected to something. What is it connected to?
Carbon.
Carbon. What were we studying again?
Carbon.
Carbon. Organic chemistry was the answer I wanted, but carbon works perfectly well. Okay? Because the follow-up is then, what is organic chemistry? Well, it's the study of carbon. So our very first simplification is we delete carbons from our symbol, and we assume at any point there is a carbon atom. Every line has 2 points. Okay, so we have a carbon. So I have a carbon bonded to an oxygen. If I have a carbon bonded to an oxygen, I have a polar covalent bond, because that's anything bound to oxygen, nitrogen, or a halogen. Okay, so cool, that bond is there. I showed the top one in blue, meaning it could have been a different connection, right? Except if I look at that one, it's oxygen to carbon, which means that bond is also polar covalent. Why is it special or different from the first one we looked at?
It's a double bond.
It's a double bond. What we will discover is the term double bond is a very bad term. It hides a bunch of information. That's going to be next week. Okay? Fair to look at now. Or not fair to talk about now, but we'll address it later. So what is this point?
Carbon.
Carbon. Okay? And now I got to get real nuanced here. Everybody see right there where I'm pointing? That little dot right there? That is a carbon. Is that also a line? Yes. Is that another carbon?
No.
No. Those two lines are pointing to the same point. It's just a larger point. Everybody okay with that? Okay. So I have a carbon there. Which means, what kind of bond do I have between that carbon and carbon? Double.
Oh, wait, that one?
Sorry, here in blue. I was wondering why you said double, but yeah,
Covalent?
that would now be a covalent bond. Okay? Because it's a carbon to carbon. I said this drawing has all of these bonds on it, including carbon to hydrogen. Does anybody see a hydrogen? What the hell? Okay? So let's do a little dance further away. Let's move along that double bond up to that point. What do we have at that point?
Carbon.
Carbon. Okay? And we're going to make that an orange carbon. That orange carbon right now is unique and different from the black carbons. How? Correct, it's orange and the other one's a black. Try again.
Because of the double bond? The second line?
Right. Find something else.
Does it actually have electrons you can't see in that? Or
No, getting towards the right idea. That was a really good observation, by the way. I didn't see that, just so you know.
It's got hydrogens bonded to it.
How do you know that?
Because it's not, doesn't have its, what's it called? Octet rule.
Okay, so you're pulling at octet rules, which is lovely. That's Lewis structure. We're about to do that. We actually addressed this without using octet rule. How many bonds did we say should be to carbon? 4. How many bonds do we see to this black carbon? 1, 2, 3, 4. So I don't like double bond, because everybody goes, it's now quote unquote a single bond. It's not a single bond, it's the combination of 2. That black carbon has 4 bonds to it. How many does this one have?
4.
4 bonds. How many does this one have? 3. That can't happen. What did we do? Exactly what Ty was suggesting. There's a hydrogen there. Ty said hydrogens. How many hydrogens should be connected to that carbon? Why 1? It has 3 bonds, which means it needs a 4th bond. It can only add 1 more bond to a hydrogen. There is 1 hydrogen connected to it. That hydrogen is implied. Why is it implied? Because we will assume that our atoms have satisfied their octet, have satisfied their 4 bonds, okay? And we have to nuance the 4 bonds later, okay? And if it doesn't explicitly show all of those bonds, there's implied hydrogens behind it. Okay? Dang, isn't that brutal? I said it showed everything. It doesn't show nitrogen or halogens. I lied. Make sense? Cool. When are we done? 1:15? So what we've now kind of set up is this larger now overarching picture of all of these kind of moving pieces. And now what we really need to do is start to kind of drill into details. Okay? And those details are really going to start with making sure you understand the fundamentals of Lewis structure. Okay? And that's what the Lewis structure play posit is about. Okay? This is the video that I make all Chem 130, as Lynette will attest to, students watch. Okay? Because I want students to follow this bonding pattern on how you structure things. Okay? There are plenty of other methods to drawing Lewis structures. Okay? So background information, electronegativity, bonds are different. We just evaluated this Lewis structures. This is kind of theory on where it's coming from, yada, yada, yada. Yada, yada, yada. There's our rule set. Okay? I break it down as 7, depending on how I count. Sometimes it hits 8 different rules. These are the rules you should follow to draw any and all Chem 130 Lewis structures. When we move up to OChem, these fundamentals still need to be there so that when we scale up to larger structures, we don't make silly mistakes or miscounts in how we process things. Kind of, sort of? Because this is such a fundamental thing, that's why I push it now, so that we don't have to worry about it as much later. Kind of, sort of? Okay, so overarching process, we want to know our valence electrons. We need to pick a center atom based off of electronegativity. Right? We'll add our electrons around our structure to the most electronegative atoms. That becomes a really important differentiation between my method and most others. What was electronegativity?
Ability to take electrons.
The ability to take electrons. What is Lewis structure talking about?
Bonding of electrons.
Bonding. So if I'm now going to put electrons into a skeleton of atoms to decide where those electrons should go, where should I place them by priority?
The most electronegative.
The atom that is the most electronegative should vacuum up all the electrons first, and then they should get scattered accordingly. Okay? If we follow those fundamentals, that allows us, and it sets us up in a place where we can encounter the reason for this principle, okay, which is resonance. I think this used to be an A, but in the copy-paste issue, it shifts it around. Okay? Resonance as a phenomenon should be addressed in Chem 130. It may not have been, and it usually is not addressed in a way that makes any sense to any student. Right? Are we willing to do like a straw hat poll here? How many people heard of resonance? Okay. That's fine. So we're looking about half. I noticed that hand didn't move, Lynette. Thank you.
Oh, I didn't.
Okay. But just because it was talked about doesn't mean it's stuck, because you don't apply it. You don't use it all that much. Okay? It's usually just a one-off, like, oh my God, what the hell's going on with that? Oh, I got a question wrong on the exam, and now I don't have to worry about it again. So don't freak out. But resonance is huge. Okay? It's probably one of the biggest drivers of organic chemistry. And so we will constantly be going back to it and reusing it. Okay? The last part in Chem 130, okay, you could just assign your non-zero formal charges as a symbol in the upper right-hand corner. Okay? You officially were not responsible for saying this atom is charged. You said the molecule was charged. Some instructors vary that. Okay? But that's the official policy, at least at Chandler Gilbert. Okay? In organic chemistry, because we're talking about how carbon bonds and where the electrons are located, we must be very specific. And we have to say exactly where all the electrons are. So we will have to assign formal charges. Okay, so that's going to be a new shift for us. So the rest of the video then pretty much goes through and says, here's some examples. Let's work through some examples together. Okay, where it will pop up with questions. I don't think these ones are as annoying. Okay? Then it pops up with this thing, because again, it's targeted towards Chem 130, and then it addresses these two new concepts. Okay, follow afterwards. This formal charge thing, guess what? We're not in Chem 130 anymore. You're now responsible for doing this formula calculation. It's a relatively simple formula calculation, so don't freak out too much at it. You will also find you can memorize your structures so that you don't have to worry about it. Okay? And then the last one, the quality of your Lewis structures. Because there will be cases where you could draw multiple things and you have to decide which one is better than the other. There's rule sets that dictate that. It starts with octets and then minimizing charges. Okay? So if you encountered exceptions to the octet rule in your Chem 130 class, let's try that actually. Did anybody encounter an exception to the octet rule in Chem 130?
You mean like with hydrogen?
So an atom that exceeded its octet.
Yes, depending on that work.
In Chem 130, or did you take Gen Chem?
I did one thing.
You did 130? Interesting. Most instructors don't talk about it because usually they don't understand it, is quite frankly what it comes down to. Okay. So there are cases where we can exceed octets, and it's coming from ranking structures. Okay? After that, we move into kind of shapes, things that you have to understand where things are located. We'll address the shapes in a little bit. For instance, when we look at methane, there are 4 bonds. Those 4 bonds are all identical to each other, right? Which means if they're all identical, what should the angle, how far away from them from each other should they be? Should it be the same or different? It should be the same, because they're all identical. And yet, are they all identical in this drawing?
Yes.
Yeah?
On the drawing.
This hydrogen right here to that hydrogen. Is that the same as this hydrogen to that hydrogen?
No.
Ooh. Does the drawing accurately reflect 3-dimensional model?
No.
No. And that becomes one of kind of our reasons for why we manipulate things in art. The GIF here is showing the actual shape. That's where we introduce wedges and dashes to represent that shape and that relative positioning better than a standard Lewis structure. Note better, not perfect. Okay? We'll see valence shell electron pair shapes. We're officially responsible for shapes. You do not need to worry about this group at all. Almost everything we're going to do has been sitting in the tetrahedral category. Okay. What we'll find is that there's a difference between bonding and non-bonding, and that's going to dictate different lines. So really what you're going to be responsible for shapes is right here. Tetrahedral, trigonal, pyramidal, and bent. That's our home. Those three shapes are going to be critical to us. Why is it critical? Do I need to know what the shape of a table? Particularly when putting a table together.
Yeah.
Yes. Okay, I need to know the legs go on the bottom, not on the top. Okay, I need to know the surface on the top is supposed to be elevated, not on the floor. Okay, all of those relative positionings are critical to understanding how we manipulate and interact with it. Organic chemistry is about how those shapes interact with their world. We need that information. Okay, so one of the things that we're going to have to get comfortable with is how do we represent our drawings and what those representations mean in a three-dimensional world. That is very challenging to deal with. Okay, shape summary. Okay, this is where it now boils into dealing with formal charge and oxidation state. Ignore oxidation state. I think the video will tell you to ignore it too. Formal charge is where we're going to sit. So we've got our formula there. Formal charge, going through and looking at our structures. Okay, and that would kind of get us here. Okay, so provide the Lewis structures for sulfate and carbonate. Okay. For the sake of kind of importance, what I really care about is the structure for carbonate. So if we were going to follow through this, how would we start?
Counting valence electrons.
Awesome. How'd you know you should be counting valence electrons?
Said it right there.
Okay, cool. Could have just said because I'm awesome, Mike.
Oh,
I listened to everything you said.
I did, but it also said.
Well, always make yourself sound smarter. I appreciate it. Okay, so total the valence electrons. So how many valence electrons does carbon have? Cool. How many valence electrons does oxygen have? 6.
But there's 3.
Slow, but yes. Everybody okay with that? Carbon has 4, oxygen has 6. No remote questions. There's a lot of yeses. If there's any no's, talk to me because we need to make sure about that. There are 3 of them, so you're right. We have to multiply it by 3, which means 6 times 3, 26. Okay. At least you looked at me funny. 18. Okay. Now what?
Add the 4 to the 18.
Add the 4 to the 18. That is part of the summing, totaling. Yes, I agree. Well, unfortunately, we're missing a step.
Find the central atom.
Say it again?
Oh my.
The -2. If we're looking at carbonate, there's a -2 in the upper right-hand corner. What does that upper right-hand corner denote? The charge. How did it become charged? When we looked at carbon, and yes, anion, okay, if we're getting specific, carbon had 4 valence electrons. When did it have 4 valence electrons? When it was neutral. When did oxygen have 6? When it was neutral. If I take 4 neutral atoms, carbon, 3 oxygens, what would the charge be? Neutral. It's not neutral because it says -2, which means what do I have to do?
Add 2 electrons.
Account for that with a charge summary. We're going to add 2 electrons, even though it says negative. Why? Why do we add when it says negative?
Electrons are negative.
Awesome. Okay. 2 and 18, 20 plus the 4, 24, assuming I did all the math right. We pick our center atom. The center atom is our least electronegative, carbon. Oxygen is further to the right than carbon is. Okay? We can now scatter my oxygens around it. Where you scatter them is ultimately irrelevant. The general pattern that I would push kind of behind Lewis structure goes back to its theory. It was based on cubes. So if you draw a square around your center atom, place your oxygen on a face of that square. Oxygen, oxygen, oxygen. Next step, place electrons. The electrons we will place on the most electronegative element. Which atom is the most electronegative?
Oxygen.
Oxygen. There's 3 of them. It doesn't matter which one we pick. Which one do you want to pick?
Top one.
Wrong. Let's do the left one. That was a trick question. Top one. Where do I want to place those electrons? Same deal. Think of it as squares. Okay, so place them on the faces of squares around that oxygen. I would try to, though I usually fail at it, place the electrons where I know they need to be. I know they need to be between the oxygen and the carbon. Why?
Because they're going to bond.
They're going to bond, and that's where they're going to share electrons. Okay? Then I will place the electrons on the other faces. I've added 8. You made a face question? Okay. Now I can move to the next one. Same deal. 8. Another 8. How many have I added?
24.
24. How many was I supposed to add? 24, which means I'm all good. So now what I can do is convert pairs of electrons into bonds as a line connecting the atoms. Okay? You may have had an instructor go through and delete pairs and turn all pairs into a line. Did anybody have anybody do that? Good. You had younger chemists. Dang, that was recorded. Now what do we do?
Brackets and charge. Doesn't carbon need 2 more?
Says the woman that was like, oh, you just do it because of step 1.
That's my bad.
Step 6, satisfy octets, which means we have to check octets. We placed electrons in pairs at 8 to our oxygen atoms, which means, do we need to check the oxygen atoms? Your choice. Generally, I'd recommend yes, but we don't need to check them officially, right? But what we should check is the carbon. How many electrons are on the carbon?
There's 6 right now.
There's only 6. Okay? Because there's 6, I have not satisfied the octet. I need 8 electrons around all atoms. Okay? The way that we do that is exactly specified here, by moving pairs of electrons. We don't add more electrons because we've already accounted for our total. We're only allowed 24. Okay, so I can't put in another pair. I can only have 24. So what I have to do is move electrons that are here. So anywhere I have a pair of electrons, I can move them such that the carbon can satisfy its octet. The question becomes, how do I move them? So let's go ahead, because you said top, and I was a jerk. Let's remove a pair from the top oxygen. I'm going to take that pair, and I'm going to put it on the carbon. I've moved the pair. I'm following the directions. Right? Is the carbon now good? Sorry, people were drawing. You shouldn't have drawn that. Is the carbon now octet?
No. Well,
Is the
technically, yes.
carbon now octet?
Yeah.
Yes, the carbon is fine. We did fix the carbon. But at what cost?
The oxygen isn't.
The oxygen now doesn't have its octet. So moving those electrons was the right idea, but I have to move them in such a way that I don't break the other atom's octet. Where can I place the electron so it doesn't break? I can place it as a pair between the atoms. Now they both have equal access to it. But because it's now a pair of electrons between atoms, what can I do? Turn it into a line, and what have I now formed? A double bond. That's the existence of double bonds. They don't just I need a double bond. There's a reason for it. It's because of the octet. If you follow these rules, that reason kind of naturally appears. Carbon is missing its octet. That's why I need a double bond. It's not just someone says you need a double bond. It doesn't work that way, and that's why I'm frustrated with how it gets taught in other places. Okay? But this method also brings in an interesting dilemma. Let's rewind back. Too far. We said the top oxygen. Why are the top oxygen's electrons any different than any of the other oxygens?
They are
They aren't. What does that mean?
resonance structures.
I could have moved them from the left. Okay? That's resonance. What we're saying is that central structure that I drew, that I started from, had multiple outcomes for how I could have drawn it. I'm going to ignore all the electrons around it just because it's tedious to draw them all. But I could have had that scenario, or that scenario. I know those are kind of close and small. Are we okay with how I drew those? Okay. Are those different?
Yes. Well, no, but technically yes.
And that's where we run into this weird gray area. You're like, well, isn't the relationship between these two that I just took this one and I flipped it over? I like that observation, but no. Okay? When we're considering resonance, our structure gets pinned. Imagine the frogs in biology where you pinned, everything's down. Worms? Is that better? Did you not do that in biology either?
I did a fetal pig.
I would prefer frogs and worms, but okay, if you're pinning the things down so you can look at the insides, that's effectively what's happening with resonance. Once we're here, we pin, can't move. Now, how could the electrons possibly move around? That's what's generating each of those new structures. New structures. Which of those structures is the correct structure? It's a weird paradox. It is not all of them. It is not none of them. Okay? Or not each of them. All of them together as a bucket whole have to be considered. They're all part of it. These are effectively our probability clouds that we talked about earlier. They're equal probabilities for existing. How do I know they're all equal probabilities? Well, that goes back, remember I said the added thing that we have to deal with is best versus useful or best Lewis structures. And deciding best, we would have to check octets. They all have the same octet. They all have the same formal charges, which means they are all equivalent, which means if I ask for the Lewis structure for carbonate, you draw 3. Does that suck? Yes. Okay. Why do you need to do that? To get used to the pattern of recognizing how electrons move. Okay? Kind of makes sense? No, dang it. Okay. So, resonance is the ability to arrange the compound's electrons. It is only electrons. So if we looked at that structure, or all of those structures, what happened to that pair of electrons? It's kind of a weird statement. It never changed. Really what we talked about doing is where the double bond appeared, where the second line of the double bond appeared. The first line never moved, because if I move that, what happens? I've broken the atom connection. The atom is moving. I'm not allowed to move atoms. So the only thing I can move are electrons, and there's only certain electrons I'm allowed to move. Turns out they're going to be the non-bonding electrons and the extra lines. We'll call it the green line here. Those are the only electrons I'm allowed to move. We'll come up with better names for those once we start doing a little bit more digging into the hybridization and all sorts of other fun stuff. Okay? With that, I would love to keep talking, but I'm pretty sure you want me to stop.